Okay, let's get started. Okay, so let's just continue from yesterday's discussion. So we are looking at actually wave here. So wave is propagating from the source, and then we have double slit here. Okay, two holes on the wall, and then we are essentially detecting, how the wave arrives at the detector set. Okay, so the first case and second case, where the one hole is closed, then we get actually kind of the probability of arrival is essentially kind of same as particle. But once we have two holes open, now we are seeing some interference patterns, okay? Like the way you see here, okay? So then we are going to basically try to understand why that happens, okay? So then, as a wave kind of since the wave is a kind of equal distance from those two holes, wave is going to arrive at these holes at the same time, and then basically if we target, or if we just kind of look at this point, we can actually kind of estimate what is the distance between this point and the hole 1, and the distance between this point and hole 2, okay? And then that is essentially distance d1 and then d2, okay? And then these D1 and D2 are different for, basically everywhere except for just the center point, right? So, and then because of this difference, okay, because of this different traveling distance of the wave, we are going to have some interference effect, okay? So then, we are going to actually see when we have the maximum values, that is essentially what we are looking at here. So if this D2 and D1 have multiples of the wavelengths of the wave, right? And they can be multiple, okay? So in that sense, N should be 1, 2, 3, 4, 5. So what that means is that we can actually kind of, schematically draw the wave, okay? So for example, this one is essentially going through number 2 hole, and then this one is a wave going through number 1 hole. Right? Obviously, D2 is longer for this point, right? D2 has a longer distance traveling, and then number 1 hole, wave going through number 1 hole, has a shorter traveling distance. And if the travel distance difference, okay, is just like 1 lambda for this example, we have complete constructive interference. Does that make sense? Okay. So in the sense, it can be 2 lambda, right? It can start from this point, right, and then or 3, 4, 5. If that is, as long as that is multiples of lambda, we'll get the complete constructive interference, right? So that is essentially, how we can understand why we have a maximum. And then, for this case, we are just looking at this point, right? But we can evaluate this point, and as we move away from there, the difference between D2 and D1 is going to be larger and larger. Does it make sense? And then because of that, we are going to have this n times lambda, okay? And then we are going to have these ripples, okay, like that, okay? Like going up and down. So we actually found out why we have the maximum values here, and then we can also look at when we are going to have a minimum values, right? So that is essentially, we can kind of evaluate that. That is essentially when we have D2 minus D1 is essentially 2n minus 1 lambda okay, or this one is essentially 1 over lambda, 3 over 2 lambda, or 5 over 2 lambda, and so on, right? So if that is a half wavelength, then we are going to have out of phase, right? So in the case, basically, I'm going to just draw one more time here. So here, let's say, going through this one is, now this one is through number 2 hole, and then let's say this one is now, if I draw the exact half, and then this one will start from here like this, right? So in this case, my point here is that this one will be essentially D1, and this distance is going to be D2, right? So if this D2 and then D1, the difference is just, 1 over 2 lambda or 3 over 2 lambda or 5 over 2 lambda is completely out of phase. And then when we sum them up, right, this way it's going to kind of arrive at the detector point. In this case, let's say here, then we are going to have destructive interference, right? So in this case, basically again here, constructive interference, and in this case we are going to have destructive interference. So we are going to have minimum values, local minimum, okay? And then this one we are going to have maximum value, okay? So in the sense, like as we actually move the spots, away from like here and then we're going this way, there will be some differences of D2 minus D1, and then depending on this constructive and destructive interference, we are going to have the amplitude change, right? That is why we are going to have here the varying values from here to here. And then, like we have a local maximum, local minimum, local maximum, local minimum, local maximum, and local minimum, right? So that is essentially, how we can understand this interference pattern, okay? Okay, so this is essentially kind of what we expect for particle and wave, okay? So, wave and particle behave very differently, right? I mean, this one, I guess we can kind of understand relatively easily. But here is a very interesting part, okay? So let us look at electron, okay? So in this case, we prepare the same setup, okay? We prepare the same setup, and in this case, we prepare electron gun, okay? So electron is actually quite small, right? And then this is the gun, which is shooting the electron, okay, not bullets. And then we have again 2 holes here. Okay, number 1 hole and number 2 hole. And the way we are performing experiment is like this way. Okay, we are shooting 1 electron at a time. Okay, we are shooting 1 electron at a time, and then we wait until that electron arrives at the detector. Okay, and then we do this experiment 1,000 times. Okay, so then what would you expect, when you open both slots? Okay, so obviously, now we can kind of easily guess when number 2 hole is closed. That is essentially, this is what we get, because this one is, this one doesn't change whether that is particle or wave, right? And then, when number 1 hole is closed, and then obviously this one is number 1 open, number 1 closed, and number 2 open. So in this case, what we get is something like this. Okay, this one is for that, and this one is for that. Okay. But what if we open 1 and 2 both open? What would you expect? Again, experiment here. We are shooting 1 electron at a time, and then we wait until that electron arrives at the detector. So what would you expect? Just like a particle case, right? So that is, what most people assume and also kind of anticipated, right? Because, obviously we are shooting electron 1 at a time, and then we'll wait until it arrives. But the experimental result was kind of surprising because that one just kind of showed like a wave, like this. Okay? So for example, this is essentially kind of experimental result that scientists got a long time ago. Let me just kind of copy that and then we'll just 1 second. So I can kind of show you here, okay? So again here, if I zoom in here, so electron beam gone here, and then we have 2 holes there, okay? And then we are shooting 1 electron at a time, so like this one has like a very low number of counts, right? It's basically some points here. And then as we do this experiment thousands of times, okay, and then you kind of see the wave interference effect, right? You guys see that? If that is just kind of particle-like behavior, you are gonna see only 2 peaks, right? Or 1 peak or just 2 peaks. But with electron, when we did a double slit experiment, we were seeing, multiple peaks, okay, more than 2. So it was a really kind of behaving like wave, right? So that one was kind of surprising, yeah. Why is that? Because, because we are shooting 1 electron at a time, and then individually we kind of see that it arrives 1 kind of spot at the backstop or at the detector at a time, right? We kind of see, okay, we are seeing just kind of 1 spot after we shoot an electron, but as we build up, multiple experiments, we are seeing interference effect. Okay, so that one was kind of surprising part. And then people later on, they call it actually wave-particle duality. Have you guys heard about that? Wave-particle duality. So it has kind of both features at the same time. Okay. So here, let me just kind of write down. This is a kind of a very interesting aspect, and then we are gonna kind of cover this one in this class. Okay, wave-particle duality. Okay. What does it mean? Like a first, electron arrive at the backstop 1 at a time, like a particle. Okay? So wave does not behave like that, right? Like, but particle behaves like a particle because when we shoot electron, it arrives at the backstop 1 at a time. Okay, but it also exhibits a wave property like probability of arrival is subject to interference, like wave. Okay, so this one is also very interesting. Kind of back then, even now, it's very interesting. And also, like we can also even ask for this particular example. It kind of shows wave interference effect, and then one can ask, do we know then which hole the electron goes to? If it is particle, we know for sure electron is going to go through either number 1 hole or number 2 hole, right? Does it make sense? But now for this electron case, at the end of the experiment, we are seeing interference effect. Even though we are shooting 1 electron at a time, do we know whether this electron goes through either number 1 or number 2? That's a questionable, right? So in this case, we cannot really know whether electron is going through number 1 or number 2. Okay? So this is a kind of quantum world. Okay, this is essentially kind of what we are going to talk about in this class. Okay? It's kind of confusing, But this is essentially kind of failures of classical mechanics, like example number 1. Okay? Because certain object can exhibit both particle light and wave light. Okay? So any questions on this before we move on to the next example? Okay. So second example is ultraviolet catastrophe. Okay. So for this one, let me just kind of write down a few words here. So classical physics for black body radiation You guys learned about black body radiation from heat transfer, right? You guys remember? Okay. So classical physics. So like this is actually kind of theory developed, like a long time ago, or like basically, the things that you guys learn in heat transfer, that is correct one, but this is actually theory developed before that. Okay. So this is kind of incorrect. But classical physics for black body radiation back then, people believe that this is the most accurate description, that is a Rayleigh-Jeans law. And then following this Rayleigh-Jeans law, spectral intensity or radiance is given by this expression. Okay, so in this case, the radiance depends on wavelength and the temperature. Okay, so this is given as 2 pi c kBT over lambda to the power of 4. Okay, so kB is Boltzmann constant, T is the absolute temperature, lambda is wavelength, and then C is the speed of light. Okay, so this one was a spectral radiance equation. Okay, so there was a kind of theory, and then this one actually had some trouble explaining natural phenomena. That is because, like when we actually do experiment, so let me just copy and then explain here. Okay, so this is a kind of spectral irradiance. Okay, so irradiance at top of atmosphere, that is experimental result. Okay, so let me just kind of write down here. Results. Okay, so like basically radiation from sun, is essentially kind of black body radiation, and then when they obtained the experimental result, it showed this distribution along the wavelengths. Okay, so for example, very low wavelengths is essentially 0, right? And then it goes kind of up, and as we increase wavelengths, the value goes down and eventually kind of goes to almost 0. Okay, so this one was the experimental result. And then look at this spectral radiance of Rayleigh-Jeans law. How does that behave? As we increase lambda, right, this is a plot against the wavelength. As we increase lambda, this I goes to 0. So in the sense, this one is fine. But as we decrease lambda, what's going to happen? It blows up, right? So if we actually plot it, it's going to look something like this. Okay, so this one is essentially Rayleigh-Jeans law. Okay, so and then this one was a kind of a like scientists found that this is a really puzzle. Okay, because of discrepancy between experimental results and state of the art modeling. Okay, because probably at the a larger value, I can kind of I exaggerate. You can actually kind of put it this way as well. That's fine. Maybe that is a probably better way. Let me just kind of scale down. Okay, so that you kind of see this one is gonna be something like this, and it kind of blows up. Okay, so this one describes well for higher wavelengths. but below certain wavelengths, right? In this case, particularly 500. Okay, this is actually given the temperature. Okay, so below certain wavelengths, there was a big discrepancy between the experiment result and the theory. Okay, so this one was essentially kind of called ultraviolet catastrophe. Why? Because this discrepancy happens at low wavelengths. This low wavelengths, this one is essentially what? Ultraviolet region. Okay? So basically this kind of the discrepancy between experimental results and theory kind of leads to ultraviolet catastrophe. So this one was kind of a big problem. People kind of try to understand or try to find out why there is so big discrepancy in ultraviolet region, okay, for black body radiation. Okay, and then this one was kind of a long-standing problem. Okay, and to address this one, Planck kind of came up with kind of crazy idea. Okay, so back then it was crazy idea. So Planck basically, this one was a kind of a thought experiment. So solved this problem by hypothesizing that electromagnetic wave energy is quantized. Okay, this one was kind of a radical concept. He was just kind of playing with the equations, and then how can we describe or how can we model experimental results more closely, right? And then he kind of just came up with idea. So in the sense, his idea was really electromagnetic wave emitted or observed in discrete energy packets. Okay, so this one was essentially, this idea was kind of introduced in 1900, and then with this kind of just assumption, right, with this kind of crazy idea, he formulated energy of electromagnetic wave has to be n times h times nu. Okay, so n is integer. It has to be 1, 2, 3. Okay, it cannot be any kind of numbers between integers. Okay, and then h is Planck constant. And then nu is the frequency of electromagnetic wave. Okay? So energy of electromagnetic wave, this h nu will be given, right? I mean, depending on which wavelengths you are dealing with for electromagnetic wave, because frequency is essentially kind of wavelengths, right? I mean, the inverse of that, right? So basically, h is constant. And then, for a fixed frequency of electromagnetic wave, or for fixed wavelengths of electromagnetic wave, the energy can be increased by only these integers. Okay? So, basically energy is discretized. Okay? It has a discrete value, right? It's not continuously increasing. It has to be 1hv, or 1h nu, or 2h nu, 3h nu, 4h nu, etc. Okay? So with this kind of crazy idea, he actually followed new derivation of spectral radiance, and then this one basically leads to Planck's law, okay, which is now this radiance is given as 2 pi h c square over lambda to the power of 5, 1 over exponential hc over lambda k bt minus 1. Okay? So now let us look at this Planck's law. Okay? So what happens, when we have, when we increase lambda? Okay? Let us kind of analyze this equation. As we increase lambda, this one blows up, right? And then 1 over infinity is essentially 0. So this one is a kind of a, negative 1, or, yeah, right? And then this one goes higher, so it's essentially kind of going to 0, right? As we increase lambda. And then now, what happens as we decrease lambda? That is essentially where we had a problem with the Rayleigh-Jeans law, right? As we decrease lambda, now lambda is in denominator here, right? So lambda decreases, and then this one goes, obviously this one goes smaller and smaller, right? Yeah, this one, okay? So lambda goes down, and then, this one goes kind of a, let me see, lambda goes down, goes big, right? So basically it goes big, so it basically, this one is kind of growing faster than that, so this is why it's essentially kind of leading to 0. Do you see that? So with this one, now it actually takes care of problem, right? Because, with that, actually now this one at lower value, now this one is essentially kind of dampening down, okay? So essentially, this is what we actually learned in heat transfer now. Like for black body radiation, we talk about this Planck's law, okay? So leading to T to the power of 4, okay? So for this one, this one came out with just kind of a crazy idea, okay? At the time, there was no kind of experimental evidence, or there was no proof that this one has to be true. A Planck just kind of create this idea and then follow through this derivation, and it turns out, okay, it agreed with the experimental results. Okay? So, that one was kind of promising, but, people kind of still doubt it, whether that is just kind of a coincidence. Yeah, just a miracle coincidence. So, people didn't really believe that this is a kind of acceptable idea. Okay? It was just kind of turns out, okay, this is one possible scenario that can give the results that explains the experimental results. Okay? So in the sense, this one is essentially, at high frequency or low wavelengths, the probability of emitting such high energy quanta vanishes. Okay? Because at high frequency or low wavelengths, look at this energy. Okay? This energy. This energy is relevant to frequency, right? At low wavelengths, that means high frequency. So in the sense, h nu has a higher value at higher frequency, and then we are not going to get into details, but probability of emitting such high energy quanta vanishes. Okay, so there is actually kind of probability equation for that, but as an intro here, we are not going to get into that. Okay, so this is essentially kind of the acceptable theory now, and then this is essentially what we learn in heat transfer. And then with that, you guys probably also covered this Wien's displacement law. Okay, so with this Planck's law, we can also obtain, just 1 second. Yeah, this is essentially Wien's displacement law. Okay, do you guys remember Wien's displacement law? Okay, so this is essentially, like for blackbody radiation, it actually increases and then decreases, with respect to wavelengths. The peak of the wavelengths, okay, the peak radiation just follows the temperature of the blackbody, right? So basically, this lambda peak, okay, the wavelengths of the peak of the blackbody radiation curve times temperature of blackbody has just constant. Okay, so what that means is that as you increase the temperature of a blackbody, this lambda peak, or basically wavelengths of the peak value decreases, right? Or as you decrease temperature, this lambda peak increases. For example, let us look at this 6,000 Kelvin blackbody and then 3,000 Kelvin blackbody. And then 6,000 Kelvin goes here, and it multiply by this T, lambda peak has to be this value. So lambda peak, it turns out that is a 483 nanometer. Okay, but for 3,000 Kelvin blackbody, the maximum radiation happens at this lambda peak, which has to be 900. About 900. Okay, so we have to kind of multiply by 2. Okay, 966. Okay, so like if you look at it, for 6,000 Kelvin, that is essentially approximate sun temperature. Okay, sun temperature is about 6,000, and then if we get blackbody radiation, that is essentially ideally the blackbody radiation spectrum. Okay, so then when you look at the peak radiation, that is essentially around which electromagnetic spectrum? Visible spectrum, right? Because if you look at this, maximum radiation happens at 483 nanometer. Okay, so visible spectrum is essentially from 350 to 700 nanometer, right? So like basically visible spectrum happens around the peak of the blackbody radiation. Okay, so that is essentially like what we can obtain, what we can learn from Wien's displacement law. Okay, so in the sense, like now this one is a still acceptable law, and then this one has no problem with explaining blackbody and any other problems. So if you think about this one, this quantized energy, right? This is essentially the core knowledge or core concept of the quantum mechanics. Okay, because quantum, that is essentially kind of quantized. Okay, so in the sense, the birth of quantum mechanics, people kind of agree that birth of quantum mechanics started from this heat transfer problem or blackbody radiation. Okay, so trying to solve this ultraviolet catastrophe happening in blackbody radiation, Planck came up with kind of the key concept of the quantum mechanics, and then he was able to address the problem. Okay, he kind of solved the problem. So in the sense, the quantum mechanics was actually, turned out it was relevant to like mechanical engineering. Okay, so like heat transfer. Okay, so this one was a kind of second example where classical physics failed to explain the the experimental kind of a finding. Okay, and in this case they came up with some kind of a concept that is relevant to quantum mechanics, and this modeling was able to kind of resolve the issue. Okay, so then let us look into now third example. Okay, so which is photoelectric effect. Okay, So for this one, let me just kind of describe the basic experimental finding. So when you have a light source, okay, and then when you bring the solid object here, and then this solid object, like a metal, it has abundant electrons available in the object. And then as we shine, or as we irradiate this light into the solid object, depending on the energy of this light source, the electron can be ejected. Okay? Because there is kind of incoming energy from the light here. And then depending on this energy, this electron can be popped out, and then this ejected electron is essentially called photoelectron. Okay, because that is the electron popped out due to the light. Okay, so this is a photoelectron, and then in order to understand this photoelectron effect, we need to introduce a concept called work function. Okay. Work function is the energy required to eject an electron from a solid object. Okay, so for example, like this electron is stable, right? This electron is essentially bound to nucleus, and then those are in stable form. So we have to input sufficient energy to break that bond. Okay, and then that energy is essentially called work function. So this kind of defines energy required to eject an electron from a solid object, and then this is a material property. Okay, for example, this work function of gold or work function of silver is typically 5.1 to 5.47 electron volt, and the 4.26, 4.74 electron volt. Okay, so this is a material property. Okay? I'm just giving you two examples here, gold and silver, but if you look at other materials, it has different values. Okay? So here, I'm talking about this EV, or electron volt. Yeah, maybe some of you may not be familiar with this unit, so let me just kind of briefly talk about that, because we are going to talk about this unit quite a lot in this course. Okay. So for that one, let me just talk about this electron volt. And then we often write as EV, electron volt. So, this is the convenient unit of energy at a small scale. Okay, so for example, 1 EV is equivalent to 1.602 times 10 to the negative 19 joule. Okay, so this one, when you think about it, this is extremely small value, right? For classical mechanics, classical physics, we often talk about just joule or kilojoule, stuff like that. But for quantum mechanics or for small scale object, we often deal with a very small amount of energy, right? And then we don't want to write 10 to the negative 19, 10 to the negative 20, like always. So they just introduce convenient unit, energy unit, which is called electron volt. Okay. So the way they defined is this way. Okay. So first, let me just kind of introduce a basic unit here. 1 coulomb, just to recap, is 6.242 times 10 to the 18 charge here. Okay, so E is a charge of proton Okay, just this is by definition. This is how this 1 coulomb is defined, and 1 charge is essentially inverse of that. Okay, so we can kind of basically move this value to the left, and then we can evaluate that. That is 1.602 times 10 to the negative 19th coulomb. Okay, so this is just by definition. And then, to define energy, okay, this is energy joule can be obtained by C times V. Okay, in this case, this is a coulomb, and then voltage. So when we multiply coulomb by voltage, we get energy. Okay, so for small scale object, we are essentially defined as 1 electron volt is simply 1 charge times 1 volt. Okay, this is essentially 1 electron volt. Now 1 electron volt is essentially 1 charge multiplied by 1 volt. And then the way you can understand is essentially this is a energy which an electron, okay, picks, okay, the charge, right, the 1e, the electron or charge, picks up when accelerated across potential difference of 1 volt. Okay, so this is essentially like a 1 electron volt definition. Okay, the energy required, okay, for energy required for electron to accelerate under the potential difference of 1 volt. Okay. So again, 1 electron volt is actually very small value. It's just about this 1.602 times 10 to the negative 19 joule. Okay. Okay, so now we introduce this unit, and then we keep going. For this one, let us kind of look at this one. Okay, so again, this experiment setup, light. Okay, so light is electromagnetic wave, right? And then people previously scientists kind of evaluated various experimental setups, and then back then people understood that light is electromagnetic wave. Okay, so they understood that. Okay. So then they just apply the wave property here. Okay, so electromagnetic wave, and the wave property is like this one. Okay, so intensity. Okay, maybe I'll just write down. So again, the wave can be described by this simple form. Okay, as we discussed in kind of earlier sessions here. So what that means is that this wave is given by this expression, intensity of light. Okay, okay, so in this case, what is the intensity of light for this equation? That is amplitude, right? A. Right? So intensity of light is associated with this amplitude, right? How high the wave is oscillating, right? So basically amplitude, and then as we increase intensity of light, energy of the wave increases. So in the sense, more precisely, energy is proportional to amplitude square. Okay? This is the wave property. Okay? I mean, it's nothing surprising, right, in this case. Okay. But experiments showed very interesting results. Okay. So let us now kind of think about this one. Okay. So they wanted to eject photoelectrons, right, by increasing the amount of energy or incoming energy. They wanted to increase, or they wanted to generate photoelectrons. Okay? Because you know the energy has to, incoming energy has to exceed this work function, right? And the experiment showed kind of very interesting in a sense that intensity did not really affect the generation of photoelectrons. Okay? Does it make sense? I mean, what I'm saying is, are you guys following here? So here, by just using this conventional kind of knowledge of wave, incoming energy has to increase with increasing intensity or amplitude. Okay? But when they did the experiment, they increased the amplitude to increase the incoming energy. But even though they increased the amplitude, they could not generate photoelectron. Okay? So this is essentially kind of what they found experimentally. Let me just kind of write down here. Experimentally, intensity did not affect energy of photoelectrons. Maybe this one I'll just write down a little bit later once again. Maybe this is better. Okay. So let's say intensity of light high, and then they use the low frequency of light, no photoelectrons. Generated. But another experiment they did was that, you know, they actually maintain intensity low, and then they change the frequency of the incoming electromagnetic wave. Okay, they change the wavelengths of the electromagnetic wave. Okay, and then what they found was that even though intensity was low, when they used high frequency of electromagnetic wave, it actually generated they generate the photoelectrons. Okay, so basically, you know, like I'm gonna just write down here too. Intensity low, but when they use the high frequency of light, somehow they generate photoelectrons. So basically, you know, experimentally, intensity did not really affect this energy of photoelectrons. Okay, and another way to kind of saying is that, you know, like from the experiment, maybe, yeah, this one we can kind of talk about it tomorrow. But you know, like here, the point here is that intensity of light somehow did not affect whether photoelectron is generated or not. And experimentally, it was found that what matters is the frequency of electromagnetic wave. Okay, so we will just kind of leave it at that, and then we are going to continue tomorrow